This is my DIY self-driving car based on the ATmega 8 microcontroller, and in this video I will be giving a brief presentation on how I made it and how it works. Let's start with the case construction. I bought this case as a kit. It came with 2 BO motors, 2 front wheels, a rail wheel, and a battery holder and a switch. It also included these plastic encoders for the motor, but it did not come with the necessary MOC 7811 optical encoders, which I had to buy separately. These will be used to measure the RPM of the motor to make forward movements and turns. The main body is made out of acrylic, which makes it rather fragile. The construction was rather easy as the kit came with the necessary screws and most importantly a manual. Following the instructions, I was able to assemble the kit in under an hour. I started by removing the paper from the acrylic parts. Then I secured the motor in place as well as the rear wheel in place. However, the case is not CNC'd with precision, so certain part like the motor mount has a lot of play in it. This is why I applied a bit of hot glue to firmly secure them in place. Another issue with this is that there is no place to mount the servo, thus I had to make some cut out to the circular hole to fit the servo. After gluing the servo and the optical encoders in place, I mounted the ultrasonic sensor onto the servo. With this, we complete the case construction. The kit also came with a 4 AA battery holder, which I did not mount in place, as I will be using a 2S lithium-ion battery to power it. With the case construction being done, let's look at the electronics. For the time being, I made this temporary PCB to do the testing. The brain of this organization is the ATmega 8 microcontroller. This is what does all the processing, like controlling the servo and ultrasonic sensor to scan the area and detect obstacles. Not only does it control the L293D chip, which is a motor driver to control the motor, but it also reads the input from the MOC 7811 optical encoders to determine the RPM of the motors. The working voltage for all the components are 5 volts. However, I will be powering it with a 2S lithium-ion battery. This is why a buck converter is used to step down the input voltage to 5 volts. This PCB, however, is temporary. I plan on creating a proper PCB for this project. I'll make a community post once I've acquired the PCBs. Anyway, this is it for the electronics. Now let's look at the firmware for this project. Unlike my previous projects, the code for this is a bit more bare metal. Instead of using pre-made libraries for the servo, ultrasonic sensor, and the motor driver, I wrote my own drivers for them. To control the servo, I used timer 2 of the ATmega 8 to create an approximately 60 Hz PWM signal. For the motor driver, I used direct port manipulation as well as timer 1 to generate a 976 Hz PWM signal to control the speed of the motor. Lastly, the ultrasonic sensor relies on the pulse-in function provided by the Arduino framework to measure the distance. The vehicle has 2 states, one where it's scanning the area to determine the movement direction and distance, and the second where it's driving. When the vehicle starts, it starts with the scan distance function. In this function, we first make a distance measurement and check if it's higher than a minimum threshold. If yes, then we set the move direction to forward and enter driving mode. If the measured distance is less than the minimum threshold, we set the servo to 0 degree, 90 degree and 180 degree while simultaneously measuring the distance. Once the angle at which the maximum distance is available is found, the direction is changed to turn towards that angle, and then we enter the driving mode. In the driving mode, the servo is centered and the number of rotations the wheel has to make to travel a certain distance or to make a turn is calculated. Finally, the motor driver is actuated to either make a turn or proceed in the designated direction until an obstacle is encountered. Once an obstacle is encountered, the current state is changed to scanning distance. In the main file, we import all the libraries, initialize the servo, motor driver and the pins to which the encoders are connected to trigger an interrupt on the falling edge. The current state function pointer is assigned to scan distance, and void loop, the function is called. Well, this is it, the entire summary of the code and the project itself. Feel free to take a look at the GitHub repository for the schematics as well as the firmware. If you have got any questions, leave them in the comment section and I will try my best to answer them. Thank you for watching and I'll see you guys in the next one.